Okay, hello and welcome back to 20 integrals. Okay, so I've decided that this is going to be a four-part series. We're going to do 5 integrals per part, and now we are going to do a bunch of integrals now. And this is going to take it up to 10. Okay, so we are on integral number 6 of 20, and this integral is a very, very interesting one because we have touched on a bit of integration by parts earlier. Now I want to show you how to apply integration by parts to inverse trig function. So inverse trig, obviously, you may be wondering, wait a minute, but why am I asking you to do integration by parts if there's only one function? The truth is, right, think about it. Have you learned any rule in H2 math that teaches you how to integrate inverse trig? No, right? So if you can't think of any rule that you know how to differentiate or how to integrate, please don't doubt yourself. Please don't waste a shit ton of time digging through your brains for something. Okay? Just accept that this is not integratable on its own. But as you know, a lot of things become integratable by simply expressing or simplifying it in a different way. So what is something that mathematicians love to do to express something in a different way? Multiply it by 1. So notice what happens if I write it as follows, okay? It's still the same thing, obviously, because multiplying it by 1 does nothing. But look what I have now. Now, I have an algebraic function, and I have an inverse trig function. So, Liate, I have this, and I have this. So, obviously, which one is going to be u? My inverse trig is going to be the u, right? So this will be u, which means that du is going to be whatever the derivative of this is, we'll figure out later. And this is going to be my dv. So if my dv is 1, means my v is just going to be integrate 1 with respect to x is what? It's just x. You see? Do you see the vision now? So let us integrate this by parts. Okay, so I'm going to have x and then keep this function minus this is just going to be x again, v, right? Yeah, v. Now I need to differentiate u. So if we go to our formulae in MF27, the derivative of sine x or sine inverse x, sorry, in MF27 is as follows. So what if we replace this x with 4x? Okay, this is going to be 4 on top now, and then the bottom is 1 minus 16x squared. Okay, because it's 4x bracket whole thing squared. So that's why it's 1. So that's why I get 16x squared. Understand? So let's just write this over. Copy, paste. This entire thing integrate with respect to x. And then once again, the challenge in integration by parts is you can write this, but then you may not know how to integrate this monstrosity of a function. Usually, integration by parts will be 4 marks, if not at the very, very least 3 marks. So if you can get to here, you will already have gotten 1 mark out of 3. Congratulations. But obviously, we want to do better than that. So let's try to continue integrating this, okay? And to integrate this function in orange, it's actually very, very similar to things that we have already done twice in the first part. I am going to take a constant out, okay? So I'm going to take out this constant, 1/8, and you see that I can express this as follows. And then this is in the denominator. So instead of root in the denominator, I have this, and I express it as a negative power. We've done this in the previous episode already, right? And then, because I have a negative here, and it's a negative here, I want to make this a plus. You get? So, as a result, I am going to get, just use the standard form here. fx on top, and this is just going to be power half, right? So power half, I'm not going to write it as power half this time, I'm just going to straight away write it as a root. And this will be plus c. So I will get my final answer. Just simplify the constants, and I will get, oops, plus, right? Yeah, plus 1/4 root this entire thing plus c. Okay, so that is it for this particular integral. Now, next integral that I want to show you also involves trigonometric identities. So we've done some trick here, some trick here, some trick here. This is going to be our fourth integral in a row that involves some kind of trick. So bear with me. This is actually a lot of integrals in this series are going to involve some trigonometry or another. Okay, so let's get into this. Okay, this question is actually a two-part. So the original question, I'm just going to write the credit to the original question now. It's the fourth question of the December holidays package, and the original question was from Pioneer JC. Yeah, this was question 7B. So originally, right, this question had part 1 and part 2. So part 1 was find this, and it was just 1 mark. Okay, so let's do that first because we will need it for the second part, which is the integration. Now ddx of this, I think you will see why it's only worth 1 mark lah. It's going to be, I use product rule, so x keep, and then I differentiate. I differentiate sin x gives me cos x, plus I going to keep the sin x now, and then differentiate x is just 1. That's all, it's 1 mark. A sec 4 kid could do this. Okay, and then they say hence. So you need to use this result. Find the following abomination of an integral. It's really long, hang on. Let me copy it out. So, looks very, very scary. But actually, right, they originally only gave this question 3 marks. Why? Because they asked you to hence, right? So this makes it a lot easier. Because you see, this thing here is just this thing here. So, right, you have to think, why is it that they ask you to differentiate something to give you something, and then the something that you get from differentiating that thing ends up in an integral? Obviously, this is a sign that they want you to treat this as dv dx. Okay, so let me just clarify here. Basically they are saying that dv dx is this thing. Okay, and so therefore this means that v is x sine x. The reason why this part 1 is here to help you with part 2 is because they know for a fact that if they give you kids this particular function as v, and then they say, yeah, so this is dv. Now in integration by parts, integrate to find v. Can you integrate this or not? I mean, obviously this part is integratable lah, but think about it. Can you think of any humane way to integrate x cos x based on your current knowledge? No, right? So that's why part 1 is given to you as a hint to make life easier for you. Okay? And in general, your teachers will always want to make life easier for you because they also know that they can't sabo your projected grades too much. Okay? So don't overthink, just stick to what you know. So, in this case, if this is going to be my v, means the other function must be my u, right? So this is my dv, this is going to be my u. So if my u is ln x, then what's my du? 1 over x lah. And I am going to write all of that down. So, I have u dv, no, uv, v is x sine x. Sorry, it's getting late at night. and then minus, now I want to differentiate u, so I get 1 over x, and then x sine x whole thing integrate with respect to x. And obviously this x and this x can cancel, so this will just be the integral of sine x, okay? And integral of sine x with respect to x is minus cos. I said in the first part already, please don't confuse. When you are differentiating sine, you will get positive cos, but it's the other way around with integration. When I'm integrating sine, I will get negative cos. So because there is a negative cos in here and there is a minus sign here, I can just make my life easier by writing it as a plus cos x, and don't forget your plus c. Okay, your teachers have probably been nagging you about the plus c since set 4, but please don't think it's just cliche, and don't think, oh, it will never happen to me and then go and lose stupid presentation marks for it. Okay, in fact, in the front of your question paper and in the front of your answer booklet, there's actually under a small box called remarks for candidates. It says, and there's a part called inaccurate answer. So on the question paper and on the answer booklet, they already specifically warn you that things like did not follow instructions, incorrect use of notation, omission of plus c in indefinite integrals will get you minus marks. Okay? I personally have no idea why that warning is on the question paper, but please, okay, as you can see, your schools really want to make your life easier. So please don't ignore all these warnings and pointers. Okay, please be careful with your presentation. Now, next, for the other 3 integrals in this video, I want to show you, we haven't touched on integration by substitution yet, so let us do that. Now, for integration by substitution, can I emphasize that we know that we need to differentiate the substitution, right? But a lot of people forget to actually express it back in terms of the original variables. So if it's a u substitution, they give you u in terms of x or u in terms of whatever it is, and then you will just very nicely leave it in terms of u after integrating the whole thing with respect to u. And that is a perfectly human mistake to make, but doesn't mean that it's a valid mistake to make, because it will cost you marks, and losing marks is not allowed. Okay? So remember, for indefinite integrals, whenever you have a u sub, you must convert back into in terms of x or in terms of whatever original variable there was. If it is an indefinite integral, people, an indefinite integral is my answer, a function, an expression, a number. It's a number, right? It's some constant number. So obviously there isn't a question about whether you need to convert back to in terms of x or not for indefinite integral, because there is no x in the final answer. Okay, please don't make this kind of stupid mistake. As a nice gentle introduction to integration by parts, or rather revision, I hope you're watching this as part of revision, we are going to try this integral. Actually, right, this particular question, right, this was question 7b of this Pioneer JC paper. This is actually part A of the question 7a. Okay, and Pioneer JC, being Pioneer JC, they weren't too creative lah. So the integral just looks like this. And just from writing out the integral, I think you can tell what they want you to sub already lah. The question says use the substitution u equals to root x. Please don't write u as mu and mu as u. Okay, the reason why I accidentally wrote it as mu is because I've been doing too much stats lately. So please don't make the mistake, especially in paper 2 when you have to do both stats and pure in the same paper. Okay? So the first thing, actually no, let me cancel that. The first thing that I want to do is I want to differentiate my substitution. Differentiating that substitution will already get you 1 mark out of 4. Very rarely integration by substitution question is not 4 marks. So if you don't know anything in the integration question, performing differentiation already gets you 1 or 4 marks. I know it's quite funny, but if you don't know anything else in the question, please just claw back whatever marks you can claw back. Okay, so if u is equals to root x, then du dx is going to be, this is just x power half, right? So simple, and I'm going to express this neatly now. So because this is negative power, I'm going to put it in the denominator like that. And then I must express it in terms of u, right? I want it as 1 over 2u. So because du dx is 1 over 2u, this means that dx is equals to 2u du. So not only do I need to transform my function from x to u, I also need to transform my dx from x to u. My integral 这整个 expression 里面，我不可以有任何一个 x，OK？ 所有都应该是 u，OK？ So now let me copy it over. Copy, paste. Equals to all the root x I replace with u. Okay, so this is going to be u, and then instead of x, I now write u squared plus 2u plus 2. Obviously, constants are unchanged lah. And then instead of dx, I times 2u du. Okay, let me just move this down here actually. And then I can simplify algebraically. And I will simply get out of this. I'm not going to show you the cancellation because you're not a kindergarten kid. It's just simplifies to this. Okay? So just make sure my substituted integral, everything here is in terms of u. This thing from dx 我换成 du. Okay? Please 查一下。然后 I can integrate this, right? Because how can I integrate something of this form? If you go to your MF27, under the fourth page of your MF27, there is a part on integrals. Now, I will cover this bunch in part 3 of the series, but basically, another very, very big part of your topic on integration, okay, is actually dealing with these 4 standard forms in MF27. So I'm going to write these 4 forms out now. All of these are in your formula list, okay? So this is the first one. Second one concerns sine inverse. So in this case, all the A is a positive all the A's are all positive constants. No, they are constants. They don't need to be positive. I'm so sorry. Yeah, it's late and I'm tired. Okay? And also in MF27, this arbitrary constant plus C is omitted, but please know that it's there, okay? It's never not there. That would be highly mathematically blasphemous. And then these last 2 forms here, okay, actually concern both lns. So if I have x squared minus a squared, then my result is going to be x minus a over x plus a. And then if I have a squared minus x squared, this is going to be a plus x over a minus x. And of course, remember your plus c's. Now in MF27, this one they give as curly brackets, not as a modular sign. But then in the absence of the conditions that are given in the formula booklet, you need to know that because I don't know if this is positive or not, this has to be a modulus. Okay? So this looks like we are of the form, the first one, right? But instead of x, this is going to be u plus 1. So I'm simply going to have 2 times tangent inverse u plus 1 plus c. And then we are not done. We still need to convert back to in terms of x. So in this case, thankfully, our job is fairly simple. Instead of u plus 1, I simply turn it to root x plus 1. And that is it. Okay, yeah, in the next video, I'm going to do a lot more of integrals that feature these 4 forms. Because, right, a lot of careless mistakes and misconceptions can happen when you are replacing x with a more complicated function than u plus 1. Okay, this is already quite basic. there can be a lot of questions that give you a lot more room for error. Okay, so just two more integrals before we call it a day or a night, and two more integration by substitution. So let's go on to this particular integral now. This particular integral was actually from Nanyang JC, also from a promo paper, funnily enough. So the integral gives you this. And they ask you to use the substitution. It's a trig substitution. They say x equals to secant square y. So the way to the derivative of secant is in your MF27. The derivative of secant squared is not in your MF27. But we can still differentiate this. How? Because if I want to differentiate secant squared y with respect to y, I will get dx dy. I can simply treat this like a function, right? I can simply power rule and then chain rule it. So if I power rule it, it will just become like that lor. And then I still need to chain rule. So my function inside this is just going to be secant y, right? Because it's secant y whole thing squared. So by chain rule, I need to differentiate secant. And the derivative for secant is in your MF27. Secant x and cosecant x are both in your MF27, the derivative. So please don't forget that it's there. I know it's the kind of thing that seems that they won't give you because they will expect you to know it. But if you don't know it, please just flip the free piece of paper that they give you for free, okay? And then this is just going to be 2 secant squared y tangent y. So if this is dx dy, then this means that my dx simplifies to this entire thing dy. Nice and simple. Okay, now let's do the integral. Copy. And this is going to be that's silly of me, sorry. Okay, ignore my fumbling. This is going to be a bit complex, okay? So let's see if you can follow me. Now I want to replace x with secant squared y, correct? So instead of x squared, I'm going to have secant power 4y. And then x, I just replace with this. And then my dx, I'm going to replace with what I found earlier, which is this. Actually, I'm just going to get rid of the one and move this up here to save space. And whole thing differentiate, integrate with respect to y. So, this thing on the bottom here can actually be simplified. If you recall your simple Pythagorean identity, very basic one that you learned in Sec 3, sine squared x plus cos squared x equals to 1, right? Now, notice what happens when I actually divide across by sine x, okay? Or rather, if I divide across by sine squared x, this is going to become one plus cos squared over sine squared is what? Cotangent squared, right? Equals to 1 over sine squared is cosecant, cosecant x squared. Cosecant squared x. I'm sorry. So this, you might recall from Sec 3 as well, is a result of the Pythagorean identity. And also, if you divide across by cos squared, instead of sine squared, you will get the following results. And you see that this is simply sine squared over cos squared is tangent squared, right? Obviously, this is 1 over cos squared is secant squared. So these two identities that you were probably told to memorize in Sec 3 lah. Some of you may or may not still have it memorized. If you have, that's good for you. But if like me, you return everything you learned to your Sec 4 teacher immediately after Sec 4, then you will at least need to be able to re-derive it lah. I'll be honest, for me, I re-derived this so many times on the spot that I can do this in my sleep already, and very fast, as you can see. So these two box art formulae here are very, very useful. Because if you think about it, right, especially the second one, because this, you may not know how to integrate. This one, do you know how to integrate? Yes. This one, do you know how to integrate? Of course. So, in addition to being very, very useful in integration itself, this formula, in this case, can also come in very, very handy if I am trying to just simplify. So this thing will simplify to, I have a secant squared y on top, right? This secant squared y, and over here secant 4y. Now secant 4 is just secant squared. So actually, right, this one and this one can actually cancel. Okay? So this is actually going to simplify to simply 2 tangent y, and then on the bottom I still have 1 secant squared y, but because as you can see, secant squared y minus 1 is just tangent squared y. So what's the root of tangent squared y? It's just tangent y. And then I found one more thing to cancel. This is fantastic. So this one can also cancel. That's great, right? And then you will see that this simply simplifies to 2 over secant squared is what? 1 over secant squared is what? Cosine squared, right? And then we did this earlier. Did we do it in this video or in episode 1? Hang on. Yeah, in episode 1, when I was going through the last integral, I showed you how to manipulate the double angle formula for cosine to integrate cosine squared, right? So we can use that now. And this is going to be equals to 1 plus cos to y dy by the double angle formula. Okay? And then now this is perfectly integratable to us. Let us integrate this. So integrate 1 is just y. And then if I want to integrate cosine, it's just going to be, of course, I need to take this half out. Integrate cosine is positive sine. And then here is the tricky part, okay? So stay with me. How do I express it back in terms of x? I'm going to actually draw a right angled triangle. May or may not just be my tired eyes, but I think good notes rendered that as a curved line. Just know that it's a triangle. Basically, if I have this particular angle, y, then by trick that we learned in Sec 2, cosine is adjacent over hypotenuse. So, we are going to simplify this, and we see that this is going to be equals to, by the double angle formula once again, which is in your MF27, sine 2y, this is going to become sine y cos y. Okay? And then if I try to express this back in terms of x, this is where it becomes useful. Okay? Because if I have y is, no, x is equals to secant squared y, right? So this is actually going to be cosine is 1 over roots of x, correct? X equals to secant squared y, y equals to, y equals to, no, 1 over secant squared is cos x, cos y. So cos y is 1 over x, yes. So adjacent over adjacent over hypotenuse, okay? And then this by Pythagoras theorem, which we learned in primary school, is root of x minus 1. Yeah, okay. So we are going to use this triangle now. I hope you follow. I'm sorry. I'm very, very tired. I hope you followed how we use that triangle. Uh, cos inverse, right? Yeah, cos inverse. So this term is this term. And then sine y cos y. So sine, I'm going to want x minus 1 over x times cos y is 1 over x plus c. So I'm just going to make that a bit neater. And that should be our final answer. Over x plus c. Yep, okay. Yeah, I'm so sorry. I lost myself a bit there as well, actually. Yeah, so this triangle, you will see it come out a lot of times. I think your tutorial 6a question, I really don't recall which question. One of the questions lah. Quite a few of the questions involving trig substitution will actually involve this triangle to express it back. So please know how to draw your triangle. And remember, when in doubt, when doing integration by substitution, performing differentiation will at least get you 1 mark. Okay? Let us call it a day after this last one. So I am going to go through one last integral by substitution now. So this particular integral is actually a lot more benign, but it is also longer and worth a lot more marks. Okay, so remember earlier on at the start of number 7, I did actually mention that when you are doing a definite integral, you don't need to re-express in terms of x or theta or whatever it is, because the definite integral is just a number, right? So it's maybe it's be simpler, but so far in indefinite integration, the only things that we have had to change are number 1, the uh the dx, and number 2, the x itself. In definite integration, there are 3 things that we need to change. Okay, the 3 things that we need to change. One of them is the x, one of them is the dx. Third one, my definite integral has what? Bounds, right? Upper and lower bounds. That one also need to change. So let us dive into this, okay? This video might end up being very, very long because I want to spend a lot of time talking about this question. So bear with me. Pause the video, take a break if you need to. I'm going to take a break now and let us dive in, okay? So our integral, where's this question from? JPJC. Okay, which is basically just PJC but upgraded lah. It says, using the substitution, x equals to root 3 cots theta. They want you to find this definite integral. Okay, so let us go by what we are familiar with. Let us at least get 1 mark for differentiating. Okay, I lied to you earlier when I said that it's very rare for questions on integration by substitution not to be 4 marks. This one is 6 marks because it's damn complicated, as you will see shortly. So if you differentiate cotangent is minus cosecant squared. Yes. Okay. And yeah, so therefore the x is equals to minus root 3 cosecant squared theta d theta. Okay, so that's the first thing that I have to do. Change the dx to d theta. Second thing that I need to do is actually to solve for my outer bounds. Okay, so the bounds now, my original bounds were what? Root 3 and 1, right? So when x equals to the upper bound, root 3, x is root 3 cot theta, right? So root 3 cot theta equals to root 3. Therefore, cotangent theta is equals to 1. And cotangent is reciprocal of tangent, which means that theta is equals to pi over 4. So theta will always be a base set angle. Don't need to overthink. Okay, so that's the upper bound done. And then when x is equals to 1, root 3 cot theta equals to 1. So cot theta is 1 over root 3. Tan theta is the reciprocal of that. So theta, just the basic angle, is just pi over 3. Okay, can? So that's the second thing that you need to do, which is to change the bounds. And then the third thing that you need to do is basic, right? Just change the x. I don't think I need to talk about that. So anyway, here we go. Brace yourselves. Let us integrate. So let us change the bounds. I have said that my upper bound is now pi over 4 and pi over 3. Okay, let's write that in. So my bounds are now like that. Okay? And then instead of 3 plus x squared, I now have 3 plus 3 cot squared theta. And then this thing, I replace my dx with d theta. Hang on, let me just move all of this a bit out. And this is going to be equals to, I'm going to factorize this 3 out now. So this is going to be 3 power minus 2. And then I'm going to express this as 1 plus cot squared theta. You will see in a moment why. And then this root 3 here, I can also get rid of this pesky constant. I can, okay, wait, let me put this in brackets for your clarity. This is going to be half cosec, cosec squared theta d theta. Now, you remember earlier on, not too long ago, I mentioned these two, right? So we've already used this one earlier. Now I'm going to show you how to use this one. Okay, so cot squared, I'm going to express everything in terms of cosecant. Okay, so I can take this pesky constant and this pesky constant out. So you will see that this just becomes root 3 over 9. And then this is going to be 1 plus cot squared theta. So by that result that we have on top, 1 plus cot squared is cosec squared. So this is going to be, oh, I'm so sorry, I forgot to include here this minus 2. So I will have cosec squared theta minus 2. And then just copy this over. So now I have expressed everything in terms of cosecant squared theta. It's easier to integrate. And then I'm going to get on to integrating. This is going to be, it will end up being just sine squared, right? Yeah, because it's cosecant minus 2 times power 1. Yeah, so it's just 1 over cosecant squared, or cosecant squared power minus 1. So that is just going to be, I take the reciprocal of cosecant squared, I get sine squared. And so because by the double angle formula, once again, I have this result which I've already shown you how to use. Now I'm going to show you how to use this result to integrate sine squared. So you see how all the results I've pointed out earlier can now be used. So this will end up being 1 minus cos 2 theta over 2 d theta. And then now here comes the good news and the bad news. The good news is that you don't need to draw that stupid triangle. I'm so sorry. You don't need to draw that irritating triangle to express it back. The bad news is that this is a definite integral. So I need to sub in all my trig values. This is very, very boring. You can click the skip button a lot of times because I'm sure you don't want to watch me just sub in trig values in silence, but okay. This is very awkward. Pi no, I skipped a step. This, when you integrate this, you will end up getting theta over 18, right? Yeah, because I took the half out. So sine 2 theta over 2. Sorry, I got ahead of myself there. Got too excited. So now I can sub in, right? So this is going to be pi over 3 minus sine 2 pi over 3 over 2. Yeah, that's it, right? Yeah, okay. And then now, time to sub in pi over 4. This will become pi over 2. Yeah, correct. And then I sub it in. The final answer you should get as follows. There's no need to expand. But yeah, this is what you do when you are asked to find the exact value. So I know this is a long video. I'm so sorry. Thank you very much for being with me. It's been quite a heavy one. We've done a lot of trig, a lot of integration by substitution. And then yeah, as I promised in the third part of this series, I am going to focus more on integrals of this particular type. So see you on the next part.